Welcome to the Absite Smackdown podcast. We'll talk clinical scenarios, interesting Absite facts, and interesting general surgery knowledge. Now, let's get to it.
Hi guys, welcome back to Absite Smackdown podcast. I'm your host Jessica, and with me today is Dr. David Cashmere. Hi Dr.
Jessica.
David.
Nice to see you again.
Nice to see you, and I'm actually seeing you because it's our first video podcast. How are you?
I'm struggling through it with you, Jessica. I think it's great. It's going to be great to use the format. Let's see how we do.
I'm excited. Please excuse the way I look, people. I'm used to the podcast where you don't see my face. So, all right, y'all. Today we are going to be talking about statistics, and I'm really going to let Dr. David run this whole podcast today because he's so knowledgeable and I just want to learn. And I'm sure most of you out there know or could contribute. And again, if you ever have questions during our podcast or about the podcast, you can email us at info@thehealthcarelab.org.
Well, thanks, Jessica. And you're right. Today we're going to talk about statistics, safety, and decision-making for the Absite. We're going to jump right to it. And I'm going to tell you, statistics, as many feel, can often be dry. I don't share that. I actually really enjoy it. It's been really useful in my career, but there are only certain statistics, certain facts about statistics that are really useful for the Absite. So like you normally say, and like the announcer normally says, let's get to it. Some of the basic definitions we need to know include sensitivity and specificity. Sensitivity is the probability that a patient who is positive on a test for a disease actually has the disease. An easy way to remember it is PID, or pelvic inflammatory disease. So the chance that a test is positive among people who have a disease, PID, that's the sensitivity of the test. Now, really, it's the number of people who have the disease and a positive test result, that group, divided by the total number that actually have the disease, the ones that are would be true positive by the gold standard, which would truly be positive. And it's independent of prevalence. That comes up a lot. So whatever the prevalence is, how likely somebody is to have a disease, if you just take a cross section through the population, that prevalence at any time is thought to be unrelated to sensitivity and specificity. Now, people argue about that all the time. There's something called conditional probability that we can talk about, but the bottom line is separate in your head, especially for the Absite, sensitivity from prevalence. Now, a very sensitive disease, as you can imagine, rules out, a very sensitive test rules out disease pretty easily. It's like the test is almost always ready to go off. So if you can imagine a test that's just waiting to say, hey, they have the disease. So if that test does not go off, then the patient is really, really not likely to have the disease because even this test that was so primed to go off doesn't. So the old mnemonic there is SNOUT, or a sensitive test is used to rule out disease because, again, it's kind of always ready to go off. It's always ready to sense disease. Now, specificity is kind of like the other side of that coin. A good way to remember what specificity is specificity is NIH, or negative in health, like National Institutes of Health. Like PID is like pelvic inflammatory disease. These things help us remember it. But specificity is the probability that a test is negative in patients who are really healthy, who don't have whatever disease you're looking for. So that's the number of people who don't have the disease and who also have a negative test result divided by the total number without the disease as determined by whatever best test gold standard you're using, the test that can tell you who really is negative. So
A lot of math.
yeah, it sounds like a lot of math. I'll show you in a second. It's really not that much. Now, higher specificity, Jessica, means that we can better rule in disease in patients because the test is really likely to be negative in truly healthy people. In other words, it really susses out really well who does not have the disease. It's not looking to go off like the sensitive test. So a specific test lets you rule disease in. If the test is very specific, and then you have a positive test, you say, wow, this test is really specific. And if the patient has a positive test, they probably really have the disease. Like sensitivity, specificity is independent of prevalence. Now let me take a second to tell you about these weird photos that we associate with this. I mean, here we have an orange that's blue. Here we have a person working on a plate. Let me tell you why. For sensitivity, it helps you to remember that the skin on the fruit here, it's blue. Okay, it's blue. There is no blue fruit, really. But if you cut the fruit open, it's actually an orange. We do this to tell you that this test is not positive for orange. The skin on it is blue. Similarly, okay, a test that is sensitive for orange, a test that when you have an orange fruit, okay, tells you it's going to be an orange, that would be a sensitive test for, hey, is this going to taste good when I juice it? So orange skin is a sensitive test for oranges. But of course, orange isn't the only color it's not specific to orange as a fruit. There are lots of different kind of fruits that are kind of orange looking, not perfectly orange, but kind of orange. So that blue orange helps us to remember the difference between helps us to remember what kind of sensitivity means. Now, if you think about it for specificity, a specific test would be used to rule in orange. The color orange, orange skin, is not specific to the orange fruit like we just talked about. It kind of helps you remember that a specific test will help you rule in whether this is an orange. Clearly, blue skin is not specific to orange. Orange skin is not specific to orange. So really not as helpful. The plate kind of shows us intent, meaning this person is specifically plating, I don't know, what looks to be parsley, basil. You're the chef. I don't know what that is. What do you think? what are they doing there? I'm not sure.
Well, I mean, it definitely looks like they're making a bruschetta pasta and just doing the pretty plating at the end. Okay, you're Italian. You should know this. I'm not the only one.
You're a step ahead of me. I just am really good at eating food. And I'll tell you that
okay, that's true.
Yeah. Here, this shows that this person is specifically plating something. Everything is where it should be. It's so specific to that plate that it could be no other plate of food, especially with the basil or whatever, sitting where it is. So this helps remind us that specificity is really good at ruling out other plates of food. They're so specific about it that this could be no other plate of food. The way this guy positioned, or girl, I don't know, this basil leaf is such that it could be nothing else. So that's kind of how it is with sensitive and specific tests. Both are independent of prevalence. Snout, sensitive tests rule out. Spin, specific tests rule in. Now, what's really interesting is, and I'm going to try to move us out of the way with our video chat. What's really interesting here is there's a classic 2x2 table. Now, not all tests are yes or no, or dichotomous tests. But to help people learn and think about it, we have this 2x2 table that comes up on like every test, often the Absite too. What we need to help everybody do is get past the letters that I'm about to talk about so that they understand the definitions and can apply it. Because when this gets asked about, it's never clear. It's never the perfect letter that you're about to hear about. It's always that you have to understand what the definitions are, or else you're not going to get it right.
The Absite Smackdown Podcast. Visit the Smackdown at absitesmackdown.com.
So here's that classic 2x2 table. Again, the letters don't matter. A sensitive test, sensitive, is PID, positive in disease. So who are the people here in this 2x2 chart who have disease? There are two of them. There are two groups of them. Now, in general, we write positive by the most accurate test available. And that is the gold standard test. There can be no better test. That may be autopsy, which isn't really practical because they didn't make it if they got to autopsy, or something similar. So A negative test is, by whatever gold standard best test, there's no better test out there. So what I want to share with everybody is, on the other side, we typically write, and sometimes you can write it up here, it doesn't matter, positive by whatever test you're using. Since you can't do an autopsy on these people, use some other test, blood work, something like that. Then there's a negative. Say again?
Like a biopsy, because that can be the most positive and the most negative?
It could be a biopsy, and what you're already kind of hinting at is that every different test, Jessica, has a certain level of accuracy, and some are more invasive to get there, but we'll get to accuracy kind of in a little bit, but you're exactly right. This could be a biopsy, could be blood work, could be some test that is a surrogate, because we can't do that gold standard test on everybody, okay? So the sensitivity here is the people who are positive in disease. That's the people who have a positive test by what you're using. Here, that's called group A, because they have the disease. The gold standard test says these people, A and C, they have the disease. But of these two groups, only the people in group A has a positive finding on whatever test you're using. This test misses the C people, okay?
Okay.
So the sensitivity here is the people who have the positive test and have the disease, A, over the quantity A plus C. Positive in disease. Who's positive? A, okay? And it's compared to all the people who have the disease, A plus C. Does that make sense?
Yes, it does.
So then specificity is really similar. NIH, negative in health. Here are the healthy people. Their autopsy or whatever is negative for disease, and it's negative, people who are negative, that's D, over the total number of people who really should have been negative because they don't have the disease. That's B plus D. So specificity here is the negatives in the healthy people. That's it. Again, remember, these are independent of prevalence. So here we talk about predictive value of a test, and that actually does depend on disease prevalence, meaning if you have a positive test, what's the likelihood that they have the disease? So in other words, if you go somewhere and you screen people for tuberculosis, or nowadays COVID, and the test is positive, maybe that COVID antibody test. Well, if you have 100 people, and really they all have COVID, and you get a positive test, well, guess what? That test is going to predict well whether they have disease, because everybody had the disease, so whatever. If you were to get so the predictive value, how predictive a test is, does depend on disease prevalence. If you had a population of 100 people and none of them had the disease, and a COVID test was positive, one of the antibody tests, then it turns out well, they still don't have COVID, very likely. Nobody has it. The prevalence is very low. The positive predictive value is the true positive tests divided by the sum of the true positive tests and the false positives. So of all the positive people with positive tests, it's the sum of true positives and false positives. Here, that would be A over A plus B.
Okay. I feel like we need to, for the people listening and watching, I keep giggling and smiling, and people are going to wonder why if they're not looking at the slide right now and seeing that it's Star Wars Stormtroopers.
Yeah, and the reason this is Star Wars, you're beating me to it. Yeah, it's Star Wars because, this fancy Stormtrooper has a cape, okay? So they have a cape among all the Stormtroopers, and that kind of reminds you that they're somehow special, and that predicts they are, I don't know my Star Wars ranks well enough for Star Wars, but I guess they're some kind of battalion commander, something like that. They have the cape. Now, if you were in a room full of battalion commanders, or everybody had a cape or whatever, it might not be so useful. So that's just to give you an idea. And I think you're jumping ahead, but the next one is pretty funny. That's the negative predictive value. That's true negative tests divided by the sum of true negative tests and false negatives. It's the chance that if you have a negative test result, the patient doesn't have a disease. So what's the chance that this lonely Stormtrooper is in a semi-Victorian house? I don't know what that is, San Francisco or whatever. No other Stormtroopers around them. there really are no stormtroopers. There's really no such thing in the real world. What's the chance that with this test, while they're wearing stormtrooper armor, that they're really a stormtrooper? Pretty darn low. So that's negative predictive value. It's pretty unlikely that they're hanging out in San Francisco, arms crossed. They don't even have some kind of gun on them, or maybe they do. There might be a blaster there. But the point is negative predictive value. Just because you're wearing the armor, and even and you're hanging out in the house in San Francisco, pretty unlikely you're a real stormtrooper. There just aren't many stormtroopers around in real life. Okay? All right.
We're going to offend so many people who think they're stormtroopers.
Well, I don't know how many people think that stormtroopers make it into surgical residency and beyond. I don't know.
That's so true.
We're not selecting for, I don't know. Okay, let's get to accuracy of a test. We can burn through these a little bit quicker now because that's the quantity true positive results plus true negatives. In other words, the time the test was right. True positives and true negatives divided by true positives, true negatives, false positives, and false negatives all added up. In other words, this is easier to see when you write it out.
Right.
True positives, the test was correct, plus true negatives, test was correct, divided by everybody.
Okay.
So if you go back to the 2x2 table, it's all the times the test was correct. It got them right. Either made sure that they were appropriately positive when they should have been positive, negative when they should have been negative, and it's divided by everybody in the table, all the results. So that's really most of the 2x2 table and how it works. And we're going to talk now about kind of what seem like some disjointed facts. This is how the review book goes, and most of them go this way. But these are things that are kind of essential and come up on the Absite. So we're going to move away from the 2x2 test and kind of move along.
Okay.
So remember, prospective cohort studies, where you have a group and you follow them through time, there's a non-random assignment to treatment groups. In other words, every study that has a prospective cohort, a group of people that you follow forward in time, they're not randomly assigned. They get whatever treatment they got, and you just got to watch it. So that's how that works. Just remember, prospective cohort study, non-random assignment to treatment group. How could you randomize them? All you did was follow them forward through time. A couple other things to know. Continuous data. Remember, data is a plural word, so data are. Continuous data are data that can be divided infinitely into smaller and smaller parts and still have meaning. It's continuous because you can draw it with a pencil without picking up the pencil, and it's infinitely divisible. So like an hour can be divided into minutes, and then minutes can be divided into seconds, and seconds can be divided into nanoseconds. It's continuous. That's very different than discrete data. Discrete data are ones that come in chunks, like red, yellow, green, a Likert scale, some people argue, where it's 1, 2, 3, 4, 5, but there's no number in between. You can't have meaning in between orange and yellow or something similar. Now, qualitative variables are discrete data that, like we just said, it is what it is, okay? It's colors, like up here. Qualitative variables are discrete data, like nominal, which are names, like colors, or ordinal, like they're on a scale, like happiness, or the Likert scale, some people argue is just a discrete data. So it's kind of important because we'll talk later maybe a little bit about sample size. You actually need a much smaller sample size of continuous data to show meaningful differences than you do with discrete data. So that's just an aside. It doesn't come up on the Absite much, but that's actually why a lot of these classifications are important. Allows you to determine sample size, what you can get, how long you're going to be recording data for to show some meaningful change, what kind of power you're going to need in your study.
Okay.
Now we'll briefly go into a couple more seemingly disjointed facts that come up on the Absite, like the analysis of variance and Anova. That's like a t-test. Students' t-test is really well known among people who go through medical school and everything. And Anova is like a t-test when there are more than 2 samples of continuous data. So a t-test is where you compare the central tendency, typically of 2 normally distributed data, groups of data, samples or whatever, and you test to see if they differ significantly one from the other, the mean median mode. Anova kind of does that, but it does it for more than 2 samples. You're comparing a whole bunch of different stuff together to see if there are important differences between these continuous data groups. So next up, let's talk about non-parametric statistics. And non-parametric statistics are for typically qualitative data, like non-numeric data, like patients' demographic data, like their nationality. Non-parametric means data that typically aren't normally distributed, and it's often qualitative data. There's not really a normal distribution for male versus female. There's just male, female. Red, yellow, green, typically not a normal distribution. So it's non-parametric statistics, often for qualitative data, and that's important. We're going to talk a little bit about, is there a shark sighted today? There either is a shark in the water or there's not, as this person decides whether to go in there. So you can't use some of the typical statistics you would use for things that are a little bit more qualitative. And then we should talk about what are called Kaplan-Meier curves. If you haven't seen a lot of these already, you will in healthcare. These are estimates of survival over time. And these are used typically for people with cancer, something similar, can be any condition, and it shows their survival over time, often by stage of disease, et cetera. Now, relative risk is the incidence in people exposed to some factor divided by the incidence in people who are not exposed. So if you want to know someone's relative risk of cancer, and it's in smoking, and it was 9-to-1, you would say, well, people exposed to smoking who were longtime smokers over 10 years have a 9 times increased incidence of cancer versus those who are not exposed. A couple other touch-up ones as we finish up. One is the chi-squared test, and that's used to determine two groups to see if there's a significant difference in the percentage or number who do or don't have some trait. So again, shark attacks on one day versus another day, where, in one day, 200 people got in the water, another day, 100 people got in the water. So how do you compare if there's a meaningful difference in who was attacked versus not? Chi-squared test will help you do that. Or to see if there's a significant difference in the number of people who have like a hemoglobin A1C less than 7 among diabetics versus non-diabetics. So the chi-squared test is a classic one to help you with that.
The Absite Smackdown Podcast, bringing you the best for your Absite review.
A couple other things that we said we'd get back to later, and here they are. One is a power. Power is the probability of making the correct conclusion based on a statistical test. It's very easy to design a test that is a study that is underpowered and won't show a difference. No surprise. If you don't have enough power to determine a conclusion, you can easily design a study that will find no difference. It's very easy to intentionally or unintentionally build a study like that. So 1 minus the probability of a type 2 error or a beta error is power. So let's talk about probability of a type 2 error and what a type 2 error is. The book covers this a little bit more in depth, but I want you to know now, a type 2 error, a type 1 error, if you had to describe it in one word, is tampering, meaning you didn't think there was a difference between two groups and you intervened. And when you did that, you tampered, you made the situation worse. A type 2 error is when you thought there was no difference between two things. You said, well, it looks pretty much the same, and oh, you missed it, and something bad happened. There's sort of a joke that type 2 errors in surgery are frowned upon, and type 1 errors not as bad. If you're not sure if they have a bad pneumothorax, they're coming in as a trauma patient, you put the chest tube in. If you find out they didn't have one, well, that's unfortunate. And yeah, there are risks to chest tubes, but it's a lot worse if you miss a bad pneumothorax or hemothorax in an acute situation. So some people argue that trauma and emergency surgery is sort of the home of the type 1 error owing to time limitations. But the bottom line here is that larger sample may increase power. I like to ask, and I've been talking for a while, now that you've heard, Jessica, about type 1 errors, tampering, and type 2 errors under controlling, do you see those issues kind of in daily life as you go around? Can you think of any errors or mistakes or times we should have done something that we didn't, and how those relate to type 1 and type 2 errors?
Well, I want to make sure that I actually understand it. So it seems like type 1 is like it feels like type 2, you don't know that there's a difference or that you're making a mistake, but type 1, you're like choosing to do it knowing that you could possibly be making a mistake. Am I understanding you correctly? Because I just want to make sure that I'm understanding what you're saying.
That's a really great point. Intent doesn't enter into it, and choice, what you thought before you did it, doesn't enter into it. There are times where I think, oh, we could really be missing something here. There may be no difference, but this patient also may have X, Y, or Z, and I'm taking that risk by leaving it alone, like a very frail patient who can't tolerate something, and you decide to leave something alone. They may have it, they may not. So I would say intent doesn't really enter into it. It seems like we are making type 1 errors with intent because I described that trauma situation where we did that. But I think when we start paying attention to it, we also may make choices where we take the risk of a type 2 error, and we do it consciously. So I just think the difference is once you've learned about these, you kind of pay attention to them more.
Okay. I was just trying to picture, because I know with COVID right now, chest tubes is just something that everyone's doing on the daily. So with you said having a frail patient's there, she may have a pneumothorax, but you're not really sure. And so making it type 1 versus type 2, is it type 1 if you don't put the chest tube in and she doesn't have the pneumothorax, or is it, I don't know, I guess I'm just trying to.
That's a really good point. So if you didn't place the chest tube and she didn't have a problem that needs one, that's not an error at all. Congrats, you did the right thing.
Okay.
It only happens when you look at the x-ray and you say to yourself, man, they're really sick and they're dying right now. And they either have an anterior pneumothorax and a chest tube could help them, or they have, maybe that's just pneumomediastinum. It's really hard to tell, but they're really sick. Geez, I'm just going to put the chest tube in. And then you put it in and they had a pneumo, it helps them. That's called being correct. Yeah. But if you put it in and there was no pneumothorax, and look, the issue did not hurt them badly. They couldn't travel for a CAT scan or anything to prove that they didn't have an anterior pneumo. And you listened and you weren't sure, so you decided, I'm going to take the risk. You put the chest tube in. It didn't kill them. Chest tube probably didn't even hurt them much, if at all. So you made a type 1, quote, error. We call it an error. But is it really an error? I don't know. So we do see that nowadays. And you're right with the COVID analogy.
Okay.
So we have a flight of beer on the slide. And we have that because you learn over time, you go to these breweries or whatever on your day off, and you want to hang out with friends one of the few times you can. And you go to these breweries and you get a flight of beer to try everything they have. And you kind of do a blind taste test. You say, okay, I've tried them all. Now give me each one and I'll guess which of their beers it was. And you get better at it until a certain point, the more of them you try, because you learn. And then after a while, of course, you go too far and you can't taste the difference. It doesn't matter. But the point is that you have tried them and you learn. And with time, the distinctions become more clear. With a larger sample, the distinctions become more clear. Let's talk about prevalence. Prevalence is the number of patients having the disease in the population at any one time. It is not incidence. Incidence is the new cases that kind of pour into this container full of prevalence. And it's higher in diseases that patients may have for a long time. You can have a disease that floats around the population and everybody just kind of has it, like often CMV and things like that people just acquire and they live with it just fine. And because it doesn't kill them, they have it longer. They get it early in life and they just kind of have it for a long time.
Okay.
That happens. Again, incidence, by distinction, incidence is the number of new cases of a disease in a given time period, new ones only. Okay, so if we have a movie theater, all the seats being filled is prevalence. The couple people who come in and take the new seats every so often, that's incidence.
Okay.
Now, the null hypothesis, and this will come up just as we close out our slides here. The null hypothesis, remember, is there is no difference between the groups you're looking at. No difference exists.
Okay.
That's important when we design studies, just like some of the other things on this slide. Oh, and here we go just a little bit more in depth to talk about type 1 versus type 2 error. Like we said, type 1 error,
Okay.
tampering. You think there was a difference? There's not. Now we're going to dress it up, and that's why we introduced null hypothesis. A much more confusing way to think of a type 1 error, but a way that it gets tested, is to say the same thing in a much more indirect way. And that is, you incorrectly rejected the null hypothesis. Again, the null hypothesis says there's no difference here. And if you reject the null hypothesis, but you should have accepted it, there was no difference. You place a chest tube, but there was no difference. You rejected the null hypothesis, which is there's no difference. You made an error. It's filled with double negatives, but tampering, you tampered. So much more, and this is the way it's usually taught, unfortunately, slightly more confusing way to say the same thing is that you incorrectly rejected the null hypothesis, and it's horrible, but that's how it's taught. That's how type 1 error is normally taught, okay?
Okay.
Type 2 error, under controlling, you thought there was no difference, and so you didn't do anything, but you should have done something, and you missed it.
Okay.
You under controlled for the problem or issue. Again, perhaps a more confusing way to say this is that you incorrectly accepted the null hypothesis. All right, now every time I get this on a test, Absite included, I have to sit there and go backward from, okay, tampering. So that means there was no difference, and I thought there was no difference, and I did something, and that means the null hypothesis, which says there was no difference, I rejected, and I was incorrect. I rejected it incorrectly. Okay, that's the answer. It's just a tough thing to do, but that's kind of how I deal with those questions every time. It helps me remember by thinking tampering and under controlling what a type 1 and type 2 error is.
Well, you said that was terrible, but I actually understand it better now from that example than the previous one.
Well, I really appreciate it because mostly that's how I've found over the years to teach it, if you really want people to learn it and understand it.
Right.
Because going backward, and we all hear it in medical school too, not just surgical residency, going backward and saying incorrectly accepting the null, and then your brain explodes, or it's just terrible. It's like The Boys, what just happened on The Boys. So, all right.
Don't give hints away
Spoilers?
for that. I have not watched it yet.
Spoilers. Okay. All right. It's also going to date this video, but that's okay because we make a new one for every episode of the book. So every volume of the book. So that'll give me a reason to update this video with you, or the next person who gives the talk will update it because now we have a reference in it that says, oh, it's The Boys, this season, and this just happened. So,
or people are going to be nostalgic and rewatch The Boys. You never know.
Yeah, like 30 years from now, right? Yeah. Like me and my Cobra Kai t-shirt, same problem. Okay. Next up, let's talk about preventing gaps in care. These arise from things like shift changes, transfers, new providers coming on call, and patients can get injured because the next group doesn't know everything right away about their allergies or things like that. And one of the ways to avoid that is structured handoffs. Checklists. I have a background in quality improvement. A Lean Six Sigma Master Black Belt took me years to get, had to take a lot of tests. Yeah. Right now in healthcare, checklists are super hot. They don't fix everything. They can really cause fatigue. They're not always a great way to error-proof. They're much better than nothing and can be really useful. But here and in the review book level, that's what typically gets talked about. Structured handoffs with things like checklists and order sets to help prevent gaps in care.
The Absite Smackdown podcast is based on the best-selling review book, Absite Smackdown, the only Absite review with an entire video review course included. Visit absitesmackdown.com and pick it up today.
Okay.
So, and here's kind of these slides are kind of funny. Here's a gap in care. Next up is root cause analysis. And here we have this tree with these really complex root system up there. And it's also called, a root cause analysis is often performed along with what's called an Ishikawa or fishbone diagram, because it looks like a fish. And it's used to investigate a sentinel event, which is an unexpected event involving serious risk of injury or actual injury to patients. And I recommend for the group looking at this, if you have time, you want to do a quick Google search and see a fishbone or Ishikawa diagram, I do it. There are different ways to do them. You label elements as controllable or uncontrollable, the kind of bones on the fish that go toward the spine, typically have classic heading names like people, staff, material, machine, method, mother nature, management, measurement. There's lots to it, but the point is that's the technique that's used often in these root cause analyses. And you get out the markers and you get the group together and you talk all about it. As we wind up here, we'll talk about the universal protocol. That's the Joint Commission protocol to prevent wrong site, wrong patient surgery. And it involves surgical site marking, where after you prep the site, that mark has to be visible. So you can't wipe it off with betadine or something like that.
Okay.
A preoperative checklist is part of it, and a timeout immediately before incision. That's all part of the universal protocol to prevent wrong site, wrong patient surgery. So this is the summary. The summary is that sensitivity is the chance that the test is PID. You can use a very sensitive test to rule out diseases or snout. Specificity is NIH. You can spin with that. Type 1 error, tampering, or rejecting the null hypothesis incorrectly. Type 2 error, under controlling. Should have put a chest tube in. There was one needed. You missed it. You accepted the null hypothesis incorrectly. Continuous data can be divided infinitely. Still makes sense. 1 minus the probability of a type 2 error under controlling is power. It's interesting. You can get this, by the way, from the 2x2 table. I'll mention it here. You can figure out the probability of under controlling or missing a difference or thinking someone was negative when they weren't negative. You can get that from the 2x2 table. You have all the information you need. So if you say 1 minus the chances of under controlling, missing someone who has a disease, you get the power. And that sometimes does get asked. Prevalence and incidents, very different. Diseases that linger a long time, higher prevalence because you don't die from them. Sensitivity and specificity do not depend on prevalence, but predictive value of a test does. And really last up, Jessica, the universal protocol is the JCO protocol for preventing wrong site, wrong patient surgery, and it has some important elements that we listed earlier.
Okay, guys. So again, this was all about statistics and helping us study for the Absite using statistics. I want to thank Dr. David for coming in and being with us again, giving this lecture, helping us all out. And I want you to remember to follow us, look us up on all of our social media. You can find us on Instagram at Daily Absite Fact. On Facebook, we're at Absite Smackdown. On Twitter, we're at Absite Smackdown. On LinkedIn, we're at Absite Smackdown. We do have the new YouTube channel, which is Absite Smackdown channel, and please like us or follow us on that. And then again, our Absite Smackdown podcast, it's on iTunes, Spotify, Stitcher, SoundCloud, and you can find it on our website, which is absitesmackdown.com. So thanks, Dr. David, so much. I really enjoyed this, our very first podcast/videocast, and I can't wait to do it with you again.
Hey, Jessica, thanks again for having me on today. I appreciate it. And I know statistics are, sometimes some people feel sort of dry, and I understand why. So I appreciate the opportunity to get the message out there and cover this one early. So it's one of the first ones we get out there, and I think it will help people a lot when it comes to the test.
It will. All right, guys, thanks for tuning in. And again, hashtag Absite Smackdown.
Thanks for listening to the Absite Smackdown podcast. Visit us at absitesmackdown.com for more great Absite facts.